let's take our first steps toward implementing some of these algorithms we've learned in a computer. Remember, the advantage of that is that linear algebra basically just has to do with multiplication and addition, and computers are better at that than we are. So we're going to do this in a program called Sage. You could install Sage if you wanted to, but it's kind of overkill to do that. Instead, we're going to run it in a browser window at cocalc.com. When you go to cocalc.com, you'll see something like this. So you want to click on Run Cocalc now. Now, you can set up an account if you want to, but you don't need to. You can just use it anonymously, and that's just fine. If you do set up an account, then you can do things like save your work and come back to it later. It might be a good idea, but you don't have to. All right, so when Cocalc loads up, and it can take a while, so you might have to be a little bit patient, you should get dropped into this, which is called the Welcome to Cocalc project. So different things in Cocalc are called projects. Once that loads up, we're going to need to start a new file. So we're going to go down here to Sage. Okay, you can see you can run all sorts of different other things in Cocalc, but let's go to Sage. All right, so this puts us in the first line of a Sage Jupyter notebook. If you wanted to, you can also go over here to Files and create a new file. And then start a Sage worksheet. Sage worksheet is sort of the older version of Sage. It doesn't matter, the result will be the same. It looks a little bit different, but the result's going to be the same. So I'm actually going to stick in the Sage worksheet because I'm a little more comfortable with that. All right, so what is Sage? Sage is a computer algebra system, so it can at least do arithmetic. You enter what you want to compute. If you hit enter, then you're just going to get new blank lines. So if you want to evaluate, you hold down shift while you hit enter. The first time you evaluate anything, it takes a while. This blinking green means it's thinking. It takes a while to wake up. There you go. 3 times 4 is 12. Of course, what's 3 times 5 is 15. You can see that subsequent evaluations are much faster. All right, so let's implement this Gram-Schmidt algorithm, which is over on the right-hand side, in a computer. Let's have a computer do sort of all the computations for us so that we can focus on the hard stuff. All right, so what does Gram-Schmidt do? It takes a basis and it turns that basis into an orthogonal basis. Let's apply that to this problem we had from before break of finding the polynomial of degree 4 or less that is most like the sine function. So we're going to be dealing with functions. So what we need to do is to tell Sage what our variables are. So if you just enter a letter, it doesn't know what to do with s, right? It doesn't realize that, maybe you meant s as a variable, but it doesn't know that. I think it's the name of something and it freaks out. So if we want to use variables, we have to tell Sage what our variables are. So let's use x, y, and t just for the time being. There's a command for that. Okay, so what are we going to do? Well, we need to start with a basis. So let's think about the standard basis for P4. I'll call them x1 through x5. So what is x1? x1 is 1, right? The problem with that is if you evaluate x1 equals 1 and you ask it, what's x1? Sage tells you, oh, the number 1. Sage treats functions and numbers differently. So really what we want is to say, x1 of x is 1. That means that x1 takes in an x and spits out 1 no matter what x is. Let's go ahead and ask it now, okay, what is x1? And you see it tells us, x1 is the function that takes an input and sends it to 1. These are two different things, 1 and x1 going to 1. Those are two different things. So we want the function version. So let's go ahead and set up the others. Let's do x2 of x is x. And the nice thing about this carriage return, right, you just hit enter, is that you can do more than one thing at a time. So x4 is x cubed, and x5 is x to the 5th, and then we hit, x to the 4th. I'm sorry. Nice thing, if you make a mistake, you just go edit it and execute again. X to the 4th. Okay, so our standard basis then, so you can name things. So standard basis is a set. Well, I guess it's a list, really, because the order matters when you write a basis down. So to enter a list in Sage or any other kind of Python, you just use square brackets and you tell me what the elements of the list are. Again, evaluate that, and let's ask, what is standard basis? Okay, fantastic. Now, Sage can, in addition to doing some algebra stuff, it can also do symbolic manipulation. It can differentiate. So, for example, let's say we wanted to differentiate x2. What do we get? Oh, well, you differentiate x2. x2 is just x. Differentiate that, you get 1, meaning the constant function. And notice, Sage knows that the derivative of a function is a function. Let's say we wanted to differentiate all of these things. One way to do that is to create a list. And what we want to do is we want to differentiate the ith standard basis element. So the way you take an element out of a list is you tell it square brackets and then where I can find it. We want to do that for each I between, and I'll say range here, 0 to the length of the list. So the way you find the length of a list is len. So let's go ahead and do that. I think we're good. Hit enter. And you can see what we've done is differentiated the first element, the second element, the third element, and the fourth element, and the fifth element. Okay, so there we go. There's our way of interacting with these, differentiating. Now, if we're going to work with this L2 inner product, we better tell Sage about it. So the way you do that is you invoke a definition. So def is how you start a definition. And we want to say, what is the inner product of f and g? That colon's important. So when you make a definition, you make the name. In this case, it'll be IP. Notice that gets turned into blue. And then you say what the arguments are. So who gets plugged in? So what is the inner product of two functions? Well, you get that by integrating. And you're going to evaluate f of x at x, evaluate g of x at x, and then integrate in x from minus pi to pi. There is the syntax for how you do integration. You can see it's pretty straightforward. But what I want to do is I want to make sure that that's the output. So whenever you define a function, you have to tell me what comes out at the very end. So the very end is, return is the word you use for that. Let's evaluate that. That's how you make an inner product. So let's compute the inner product, let's say, of x3 and x1. Takes a while because it's got to do the integration. You can see the answer is 2/3 pi cubed, which if you did it by hand, that's what you would have gotten. The nice thing here is that Sage works symbolically, so it's not doing any kind of approximation. It actually is giving you the exact answer. What else do we need to know? We need to know how to compute a norm squared. So what's the norm squared of a function? It's going to be what you get by integrating. Well, instead of integrating, we can just write that as the inner product of f with itself. And again, that's the final answer, so that's what we're going to return. And there we go. There's our norm squared. So let's go ahead and compute the first few basis elements in our Gram-Schmidt basis. So the first one is v1 is x1. Then how do you get v2? Well, according to the formula, which you can see on the right, you take what x2, and you're going to subtract the projection x2 onto x1, or onto v1. So we'll do, let's see, that's the inner product of x2 with x1 divided by the norm squared of x1 times x1. What's v3? Well, v3 is going to look like x3 minus the projection of x3 onto v1. Oh, I wrote x1 there. I should have written v1. It doesn't matter because they're the same, but let's make it easier if we get it right. Divided by the norm squared of v1, that whole thing times v1, and then you subtract off the projection onto v2. Okay, so let's evaluate that. So I found v1, v2, and v3. Let's figure out what is v3. Okay, we have an answer there, minus 1/3 pi squared plus x squared. Now, we could keep typing that out, but that's a pain in the butt. So rather than doing that, let's just write a program that does it. So we're going to define Gram-Schmidt. And what does Gram-Schmidt do? Gram-Schmidt is going to take in a basis and spit out a basis. So basis is a list. We need to know what's the length of that list, whether the very first element of the Gram-Schmidt basis is the same as the first element of b. So I access that by saying b of 0. Thing about Sage and other flavors of Python is that you index starting at 0. So the first element of a list is labeled 0. Okay, now, we're going to add some stuff to that. What we're going to do is, so the 0th index we've taken care of, so we're going to start at 1, right? So j is equal to 1, the second element, and we're going to do something to each element of that list. What are we going to do? Well, we are going to start with whatever that jth element of B was. And we're going to subtract, well, what do we want to do? We're going to subtract these projections, right? So we take the inner product of that thing with, well, what? With the previous basis elements. So I pick a basis element that I've already computed, right? So here you can see I picked, say, V1. I'm computing V3, so I take X3 minus inner product of X3 with V1. So there we go, divided by the norm squared of that same element that I've already computed, times that previously computed basis element. Now, I've got a new variable I here, a new index, and I want to do this for each I, and I want to start from the 0th one and go all the way up to, not to include j, but to do one less, right? So notice to compute v3, we had to go up to v1 and v2. Okay, so that's what I want to do, but I don't want to subtract just one of those. I want to subtract all of them. So the way that I do that is I'm going to turn that into a list. So if you can make a list like this that says you want to do this thing for each of these i's, that'll make a list of length, in this case, j minus 1. And that's going to be a list. But I can't subtract a list from a function, so I need to say what I really mean is the sum of all the elements in that list. So you go down that list and you just add all the elements up. And that's current v. So having computed that, where should that go? Well, that should go at the end of the current basis, right? So once we figure out v1 and v2, we use those to create v3. The command for that is called append. What are we appending? We're appending the current v. And then we want to loop over all the j's, right? So we start off with j equals 1, we do this, then we go to j equals 2, we do this, etc. Tabbing in Sage is important. So notice I haven't messed with the tabs at all. They automatically are provided. So I'm going to go back to this stage. So that says do these 3 lines. Okay, now having done those 3 lines, I'm done. So what I want to return is the GB basis. Okay, now let's see if that worked. Let's compute GB, sorry, it's Gram-Schmidt of the standard basis and see what we get. There we go. So there you go, we found this is the Gram-Schmidt result of applying Gram-Schmidt to the standard basis, which are known as the Legendre polynomials. In fact, let's name it, let's call it that so that we have that. So let's do Legendre. Okay, so now I can invoke Legendre, and I have a list. All right, let's go ahead and compute this problem of finding the projection of the sine function onto the. In order to compute that projection, I think it's probably best to make a general definition about what do I mean by project. So what do you project? You project a function maybe, and we're going to use a basis to do it. We know that if we picked a different basis, we get the same result of projection, but let's just say that it depends on the basis for now. So what do I want to do? Well, what I need to do is to compute the inner product of f with each basis element, divide that by the norm squared of that basis element, multiply it by that basis element, and then I want to add all these up. So let's say we start from 0 to whatever the length of b was. Again, we turn that into a list, but I don't want a list, I want a sum. So I say I want the sum of that thing. And then I'm just going to say return that. All right, so let's project, oh, and now we need a function, right? So let's set g of x to be sine x. Nice thing about Sage is Sage knows what sine and cosine are. So let's go ahead and project g onto the Legendre basis and see what happens. There we go.